A lot of movies are shot with a specific aspect ratio in mind. Here's what the audience will see, and this part is also on the film strip too, but don't worry about it. But I find it fascinating how the Nintendo Entertainment System is pretty much doing the exact same thing in the form of overscan. To put it simply, the visual output of the Nintendo Entertainment System is 240 visible scanlines. However, a real TV doesn't show every single one, and the areas that get cut off are called the overscan regions. Quite a few games actually have decorations and artwork in the overscan that they probably didn't realize would be cut off, like the mountains here in Slalom. It's pretty interesting seeing when games deliberately choose to leave the overscan regions blank where others don't. Truth be told, I could probably point out decorations in the overscan region for hours, but who cares? Let's talk oddities. There's actually a lot of NES games with garbage data hidden in the overscan area. Metal Gear has this garbage data in the upper left of the screen. Crystallis has garbage at the bottom of the screen, and in some rooms, also the top. Watch what happens when starting a new level in Marble Madness. Whoa! It's very common in games that scroll both vertically and horizontally to hide the seam in the overscan area. This typically results in pixels that would be slightly off-screen below the visible field being shown at the top. For example, this makes some storm clouds visible under the cement in Super C. This next one takes a bit of effort to explain, but the background can be broken into two parts. The character data, which graphical asset to use for an 8x8 pixel tile, and the attribute data, which color palette to assign to each 16x16 pixel chunk. Fun fact, there's a bug in the picture processing unit where it's possible to render the attribute data as tiles. This can happen in some oscillating levels of Super Mario Bros. 3 if you manipulate the scroll using lag frames. And it also just happens on the title screen of Teenage Mutant Ninja Turtles. Though it doesn't happen inside Super Mario Bros., here's what the title screen would look like if the scroll was extended to show the attributes as tiles. This also happens in Roger Clemens' MVP Baseball, and I haven't seen this documented anywhere. Possibly because nobody has ever played Roger Clemens' MVP Baseball. There's a lot of NES games in the athlete endorsement genre, and a shocking number of them have visual amusements in the overscan area. Look at what's happening in Wayne Gretzky Hockey. This awful color flickering at the top of the screen even ended up in a screenshot used in a magazine promoting the game. There's a rotating list of garbage on the title screen for Solstice, and if you've never heard how absolutely insane the title screen music for this game is, I've got a bit of a treat for you. I can't play the real thing for copyright reasons, but it sounds a little bit like this. Sorry, I just realized the antagonist in this game is named Morbius. What were we talking about again? Oh yeah, there's garbage in the overscan area. Let's talk about Pac-Man. In the overscan area, in the upper left corner, we have 1/4 Pac-Man. Actually, it's 64 copies of 1/4 Pac-Man stacked in the same spot. Why would they do that? Well, the picture processing unit has a single bit that can toggle if all 64 sprites are enabled, or if all 64 sprites are disabled. You cannot selectively pick and choose which ones to disable. But if you are using less than 64 objects, how should you go about preventing the unused ones from being drawn on screen? Well, Pac-Man decides to store them up here in the overscan area. To be more specific, Pac-Man omits unused objects by replacing the data in Object Attribute Memory, or OAM for short, with all zeros. This results in character 0 placed at X and Y coordinate 0 using palette 0. Sprites are actually drawn one scan line lower than their Y coordinate in OAM would suggest. For instance, you might have noticed that Mario stands 1 pixel inside the floor he stands on. So putting an object at a Y position of 0 ends up drawing it on scan line 1. But Tengen Pac-Man has a very esoteric bug in which a sprite is actually drawn on scan line 0. You see this brown pixel that alternates between the top right and top left corners each frame? This is caused by... And very few emulators get this right. So, with the help of Fiskbit, I wrote a test for this behavior, updated my emulator, and now I continue to make other emulator developers suffer in the name of perfection. Scanline 0 is actually awful for other reasons, including the fact that every other frame, the whole thing is drawn 1 pixel to the left of where it should be. It's terrible. I mean, look at this! The real console does this! Emulators don't, because it looks awful, but that's real! And because of the way Scanline 0 jitters, when this sprite in Pac-Man is drawn in the upper right, it's on pixel 256. but when it's in the upper left, it's on pixel 0, which is a width of 257 pixels. But that only happens for this scanline, and you can start to see why no one bothers emulating this. But Pac-Man is actually an outlier here. Storing objects at a Y position of 0 might hide them in the overscan area, but that's not where most games hide their inactive objects. Most games hide their inactive objects at a Y position of 248, 8 scanlines below the bottom of the screen. And this is why I wanted to make this video. What would happen if I were to modify my emulator to show these off-screen objects? What would we see? Well, it's actually pretty interesting. Similar to how Pac-Man has 1/4 Pac-Man in the top left, Super Mario Bros. Has 1/16 Big Mario off-screen in the bottom left. You're going to see a lot of flickering with these off-screen objects, and let's talk about why. There's a limit of 8 sprites being rendered per scanline. The picture processing unit will start by looking at index 0 into object attribute memory and check if the Y position is in range for this scanline. Then it will move on to the next index and check if that Y position is in range, then move on to the next, and so on. And the first 8 objects that are in range are the ones that get drawn. Since all the unused objects are moved down here, everything down here is competing for those first 8 slots. Here's some fun trivia. The objects at a lower index into object attribute memory will be drawn above objects at a higher index. To avoid giving some objects a higher priority than others, many games will shuffle the contents of OAM around, which results in the objects flickering when they overlap. An interesting side effect of this is what happens if there's very few objects on screen. Take a look at this Goomba in Super Mario Bros. It's being shuffled around in OAM with a bunch of empty slots. When the Goomba moves out of a slot in OAM, instead of overwriting it with some null data, the Y coordinate is simply moved to 248. This creates an interesting effect where the Goomba also appears off-screen directly below itself due to all the stale OAM data simply being moved off-screen. Let's look at this menu in Wario's Woods. This mushroom icon that's used for the cursor is actually a sprite. Notice how the cursor is immediately moved off-screen when the animation plays, and then it's moved again once the animation ends. The title screen of Wario's Woods also features a bunch of objects temporarily being hidden off-screen before appearing at the top. Just for fun, I wanted to show the title screen of Super Mario Bros. 3. I specifically noticed Luigi still moving off-screen, which I thought was amusing. Okay, one more. In Super Mario Bros., when Mario falls off-screen, he gains the Starman effect, and you can still control him while waiting for the screen transition. Neat. But why stop after just 16 scanlines? Let's double the initial screen height. This works particularly well with vertical scrolling. I think it's really cool to see how far the screen scrolls before the background values get updated. The first screen of Kid Icarus looks fantastic, but you have to remember that the middle of the screen is actually supposed to be the bottom, so it just kills you. What? And while it works really well for vertically scrolling games, horizontal games are using the other name table arrangement, so we just see the same screen twice. So instead of adding new scanlines, what if we extended the scanlines horizontally to 512 pixels across? It's honestly really cool playing Super Mario Bros. Like this. It's not quite a perfect ultra-wide experience, as you still have several pixels to the right of the screen, which are the not yet updated values that were just moved off the left, but with some creative cropping it can almost look good. There's a bit of a well-known visual bug in Super Mario Bros. 3, where the background elements moving off the edges of the screen can end up getting miscolored, and when playing the game like this, it becomes pretty clear why it happens. I also like how the roulette minigame looks like this. It's so cool. So what if we combine the vertical and horizontal extensions? Do we see anything cool with a resolution of 512 by 480? At this point, we're pretty much just visualizing both name tables and how they get mirrored. In most cases, it's really not all that different than just playing the game normally. But okay, perhaps we don't want to visualize how the console would actually draw a larger screen. We just want to see an entire level all at once with Mario running around in it. If you've ever seen a TAS on TAS videos with an Atlas encode, we're going to recreate that effect. Instead of reading from the name tables, we're only going to read from where Super Mario Bros. 3 stores the tile information in RAM. Instead of reading from OAM to render the sprites, we're going to take a look at where Mario 3 stores the sprite information in RAM, such as the arrays of object IDs, animation timers, positions, and such, and recreate the methods Mario 3 uses for drawing this stuff in our own C# code. This is entirely divorced from the actual screen rendering process, but the results are pretty great. We can see the exact moment the Koopa spawns in, despite being off-screen. Using some fun emulator tricks, we can go a little further. Here's World 1 Level 1 with 7 different TASes running simultaneously. I find this incredibly satisfying to watch. Bonus content. Let's go all the way back to the unmodified NTSC screen. Remember when I said the visual output was 240 scanlines? That was a lie. It's actually 242. However, the bottom two scanlines are part of the vertical blanking interval, meaning that the screen is blanked for those two scanlines. And while that wouldn't normally result in any side effects, there actually is an edge case that can be seen in Castlevania 2, Simon's Quest, where these two scanlines become very colorful. But why would this happen? Well, it's honestly, but I'll try and simplify because I think it's interesting. Let's take a look at this accuracy test cartridge called fullpalette.nes. There's about a dozen cartridges with this exact name, but they all work in the same way. When rendering is disabled, or blanked, wink, and the picture processing unit's read-write register, which we call V, is pointing to palette RAM, the color drawn on screen for the next pixel is whatever value is inside the address where the V register points. You might have noticed there's a handful of NES games that open up with a frame with a bunch of colorful bars on it. Here's what it looks like in Super Mario Bros. 3. That is the same thing that's happening in both fullpalette.nes, but also Simon's Quest. Rendering is disabled, and V is pointing to palette RAM. This will all come together in a minute, but let's take a look at how the data on the name table is arranged. We have a large grid of 8x8 pixel characters, 64 characters across and 60 characters tall. When the picture processing unit is rendering a scanline, it needs to read the tile data from the name table. Every tile has a specific address and VRAM, and you can visualize it quite nicely using RGB values for the bottom 3 digits. We can also split this information into the individual digits just to show what's going on. Let's take a look at the ones digit here, and I'll explain what this image means. The darker values are closer to 0, and the lighter values are closer to hexadecimal F. With the ones digit, you can see how the address is incremented for each neighboring character. The box gets brighter as you scroll to the right. With the tens digit, you can see rows of 16 characters, and it increments in an interesting zigzag pattern. With the hundreds digit, you can see how the 4 name tables are arranged. But something interesting happens when we take a look at the thousands digit. Now we're splitting every character up into their 8 individual rows. But by doing this, we have now assigned an address to every row of 8 pixels on the name table. When a scanline is being rendered, the V register is used to read the tile and color information for 8 pixels at a time. Then V is incremented and it repeats for the whole scanline. At the end of a scanline, the thousands digit is incremented, allowing the next row from the tiles to be read. This process of incrementing parts of V also happens at the end of the last visible scanline. So, at the start of the post-render lines, V will end up pointing to the pixel below the bottom left of the screen. And here's where it all comes together. If rendering is enabled, we're drawing tiles, but if rendering is disabled, we draw the backdrop color, unless V is pointing to palette RAM, in which case we draw the color that V is pointing to. Since drawing the screen updates V, that means it's possible for V to naturally end up in palette RAM at the end of a frame when rendering is automatically disabled. Let's figure out where on the name table this can occur. Since palette RAM is from the range hex 3F00 through hex 3FFF and 7F00 through 7FFF, we can visualize this as anywhere the hundreds digit is F and the thousands digit is 3 or 7. That leaves us with these rows here. So if any of these pixels are one row below the bottom left of the screen, the post-render lines will read from palette RAM. While we're already looking at the post-render scanlines, we might as well take a look at the screen border. In addition to the 2 visible scanlines below the screen, there's an 11 pixel wide column to the right of the screen and a 16 pixel wide column to the left. The column on the left is extra fun because the leftmost pixel is forcing the picture processing unit's grayscale mode. Beyond the screen borders, further to the left of the visible pixels, you'll see the NTSC color burst. Or maybe you won't because YouTube compression removed it or something, it's really dark. Here's what it would look like if it was significantly brighter. And that's it. A large collection of objects beyond the screen boundaries. You might be wondering, can this information be useful for speedrunning? Nope. By the way, my game Fantastic Fist is on sale for 80% off, or you can check out the free demo. And I'd like to give a huge shout out to all my supporters on Patreon. Seriously, thank you. And if you find more amusing examples of off-screen objects in your own research, you should share them in my Discord. And that about covers it. Thanks for watching, and take care.